Welcome to CSE 502T. I'll be teaching you formal languages and automata theory. In this lecture, I'll explain some basic definitions and terminology that we'll be using throughout this course, and brief history of how this subject gained importance and where these concepts are being applied in real world. If you have any queries regarding the course, you can mail me on given email ID. There are no prerequisites for this course. However, you should be familiar with C programming or any other programming language if you want to see practical aspects of this course, and discrete mathematics, as this course involves good amount of problems that will test your logic and reasoning aptitude. I strongly suggest that you pick up at least 2 books. That is the first one, Automata Theory, Languages and Computation by Hopcroft, Motwani, Ullman, and the third one, Formal Language and Automata Theory by A.M. Padma Reddy. Being computer science students, I'm sure you must have heard many definitions of computer science. Let me add one more to that. Computer science is a science of abstraction. That's creating right model for thinking and devising the appropriate mechanizable techniques to solve it. And automata is the study of abstract computing devices. It's not philosophical abstraction, but obtaining facts from a calculation on a paper or piece of research. And by model, I'm not referring to small paper-made models like you do for boats and aeroplanes, but to produce a simple technical description to show how something such as a process, a system, or theory works. So basically, it's aim of every engineering course to teach students to build models. Suppose we want to model an on-off switch. So there are 2 states in which a switch can be at any given time. It can be in on state or off state. And if user presses the button, that's your input here, then the effect is different depending on the initial state of the switch. If the switch is in off state, then pressing the button changes it to on state, and if the switch is in on state, then pressing the same button turns it to off state. So you can model a switch, draw 2 states, one representing on, another one representing off, and you can use arrows to show transition from one state to another state. You can show the initial state. You may even have a final state for any model. For example, if you want to model a fan that has got 5 different states, state 1, state 2, state 3, state 4, state 5, representing different speeds of rotation, and an off state, and then turning the knob will change the state of fan from one to other. For example, if you are in state 1, then turning the knob will take you to state 2, and so on. Similarly, you can model digital circuits like adders, subtractors, or flip-flops. And you can model any computing machine or computing device, even a computer. So what an automation is? An automation is an abstract model of a computer which accepts some input, produces output, and the output can be in the form of a string. It can be a binary string in the form of zeros and ones. It can be a string of alphabets. It can be a string of decimal digits, or it can be simply a yes or a no, depending on whether it accepts your input. It may give a yes output, or if it rejects your input, then the output may be a no. And it may have an internal storage, usually a stack or a tape. If the internal storage of an automation is a stack, it's usually referred to as push-down automata. And if the internal storage of an automation is a tape, it's referred to as Turing machine. So we'll study about both of these automations in our coming classes in detail. So moving towards the history. So it was before there were computers. In 1930s, Alan Turing studied an abstract machine that had all the capabilities of today's computers, at least as far as in what they could compute. And his goal was to describe precisely the boundary between what a computing machine could do and what it could not do. And his conclusions apply not only to his abstract Turing machines but to today's real machines also. So basically he laid the foundations of these computing devices. And after that, in 1940s and 1950s, some simpler kind of machines which we call finite automatas were studied, and the original proposal of this study was to model brain functions, and it turned out to be extremely useful for a variety of other purposes, which we'll see in coming slides, where automata is being used in real life, in a real world. After that, in 1950, a linguist named Chomsky began the study of formal grammars. While not strictly machines, these grammars have close relationships to abstract automata and serve today as the basis of some important software components, including parts of compilers. Where a grammar is a set of productions and each production is a rule. For example, if I say a noun followed by a verb followed by an adverb gives you syntactically correct English sentence, then if you replace noun by John, verb by eat and adverb by slowly, you get John eats slowly, which is syntactically correct English sentence, where I gave a simple rule. So similarly, a grammar has a set of productions where each production is a rule and they define a particular language. So we'll study about the classification of grammars and languages in detail in our unit 3rd. Later on, in 1969, Cook extended Turing's study of what could and what could not be computed. So Cook was able to separate those problems that can be solved efficiently by computer from those problems that can in principle be solved but in practice take so much time that computers are useless for all but very small instances of these problems. And this class of problems is called intractable or NP hard, and we'll study about them in detail in our unit 5. So all of these theoretical developments bear directly on what computer scientists do today. Some of these concepts like finite automata and certain kinds of formal grammars are used in the design and construction of important kinds of software. Other concepts like the Turing machine helps us understand what we can expect from our software. So here I have given an incomplete automation for adder circuit. You might have studied a binary adder in your digital electronic course, where we have two inputs. We can have an input combination of 0 0, 0 1, 1 0 or 1 1, and you get a sum and a carry. So sum I have shown by the slash, that is the output, and to distinguish between carry and no carry, we have drawn two states, a carry state and a no carry state. Now for example, if your inputs are 0 1, then your sum is 1. 0 1 gives sum 1, and in this case carry is not generated. So what we do is we state no carry state, that we have shown by a transition into no carry state. The arrow is going into the no carry state. Now consider your input as 1 1. So in that case, when your inputs are 1 and 1, sum is 0 and a carry is generated. 1 and 1 is 0 carry 1. So sum is 0 but a carry is generated. So what we do is, from no carry state we do a transition to carry state when our inputs are 1 1. This is an incomplete automation because I have not given all the transitions. All the transitions means we should have 0 0 input, we can have 0 0 input, we can have 1 0, and it's not only in no carry state, we can have these inputs in carry state as well. So we'll complete this automation in our coming lectures. Finite automata are a useful model for many important kinds of hardware and software. For example, the software for scanning large bodies of text, such as collections of web pages, to find occurrences of words, phrases, or other patterns like you do in search engines. Software for designing and checking the behavior of digital circuits. As I already said, adders, subtractors, flip-flops, you can always model them with the help of automata. Software for verifying systems of all types that have a finite number of distinct states, means where you have to remember something, but this whatever you want to remember has to be finite, such as communication protocols. For example, we have stateful and stateless protocols. So where those protocols where you need to remember a state, you can make use of automata. Again, automatas are used to build parts of compiler. The lexical analyzer phase, that is the compiler component that breaks the input text into logical units such as identifiers, keywords, and punctuations. It's based on the concept of automata theory. So with that, we're done with the introduction part, and we'll start with the basic concepts that are definitions and terminology required for this subject.